Go ahead and start. A compound circuit is a series circuit and a parallel circuit that are kind of together. So I'm just going to call this compound circuits. And here's an example. You have a battery source, and actually I probably need to draw this the other direction. So let's go ahead and make the long end on this side and the short end there. And we'll make the wire go out this way. The wire, there's a resistor, and then it branches out, and there are two resistors in a branch out here. So if I were to ask and say, hey, is this a series circuit? The answer is kinda. And if I were to answer, is this a parallel circuit? The answer is kinda. Um, Another way to kind of look at this circuit is to look at it like this. The voltage source begins, and then there's a resistor, and then it splits apart like this, and then goes back at a junction, and it finishes out at the terminal. Okay, so you can kind of see that this is a little bit of a series circuit because they are in line to each other, but it's not a resistor and a resistor, it's a resistor and a branch that are in series to each other. So there are ways to try to calculate how the equivalent resistance actually occurs. And the general step for doing this is to try to figure out, you want to try to make it a series circuit. So the branch in and of itself, I could just as easily say that this one and these two are in series with each other, right? And then how do you find two resistors that are in series? How do you add, like, almost said it. How do you just add them together, right? If it's in series, it's simple addition. If they're in parallel, your life is not so easy. So we can actually use this concept to try to find the resistance inside circuits, and then we could use that to find the current inside the circuits as well too. So I'm just going to worry about the resistances first, and then we'll kind of add in voltages and currents inside. The current's going to flow this direction, which, by the way, whenever you guys draw circuits, uh, notation and convention generally is that you want the current to go around in a clockwise fashion. So you can make a circuit that goes down and goes just around this way, but most of the time, if you see a circuit schematic being drawn, it's drawn to where the current is going to be moving in a clockwise direction. So it's usually going to be going out from the battery source and then around this direction. If the battery is on the other side, say the battery is on the right side or the branch, it would start going down and then across this way. So every time you see a circuit made, it's usually going to be that clockwise motion, unless people are just trying to be cantankerous just for the fun of it. Okay? So just a FYI for you guys. That's why whenever I drew it upside down at the beginning, I was like, you know what? I better do this the regular way. Whatever. So let's say that we have a 20 ohm resistor, and let's say that this one is a 50 ohm resistor, and let's say that this one is a 70 ohm resistor. We got 20, we got 50, and we got 70. And what I need to do is I need to take the parallel circuit components, and I need to find the equivalent resistance of just the parallel circuit components, and then I'll add it to the series circuit component. So I'll add it to this guy whenever we're done. So at the very end, our job is easy because we're just going to be doing plus 20. But to find the equivalent resistance, we're going to have to do, let's see here. What do we want to call that? It's not the total equivalent resistance. Um, you want to just say like 50 and 70 ohm? We gotta mark it somehow. Just say the equivalent resistance for the 50 and 70 ohm resistor, or you could also say parallel. Yeah, another way to do that is to like write two little lines down here that stand for parallel. Just write two little parallel lines there. That would stand for the equivalent resistance of a parallel line. I don't really care. Just don't call it the total because it's not the total. It's not all of them added together. It's just the parallel branches the 50 ohm and the 70 ohm. Okay, does anybody remember how to find the 50 ohm and the 70 ohm? Equivalent resistance. There was a formula that we did. You were close. It's the other way around, yeah. So it's 1 over 50 ohms plus 1 over 70 ohms. And there's one more really important part. It's equal to what on the other side? It's got to be 1 over the rec. Yeah. 1 over the equivalent resistance. Parallel. Everybody's like, why are you writing recce on the board? You're like, I don't know. It's equivalent resistance. Okay, mathy time. Since it's 1 over 50 and 1 over 70, you can get a common denominator for it, but I don't know. At this point, the fractions start to not really work so well together. I'd probably just get a decimal for both of those numbers and then just add them together. It's probably the easiest way to do it. So I'm going to take 1 over 50, and I'm going to get it as a decimal. 1 over 50 is 0.02. You just got to be careful with your decimal places whenever you do this. And then I'm going to do 1 divided by 70 in the calculator. That one is 0.143. So 0.0143. And that's equal to 1 over recce. We can add those two together. So like 0.02 plus 0.0143. That's 0.0343 is equal to 1 over recce. And to get the answer whenever you're done, keep in mind that this is like a fraction. So if I want to flip over the 1 over the equivalent resistance, I can find out what the answer is by flipping over that 0.0343. So the answer to this circuit, the resistance for the parallel branch, is going to be equal to 1 over 0.0343, which is a something. I'm going to do 1 divided by a second answer on the calculator. It is indeed so. I'm not wrong, right? So I'm just going to go, I bet I could need to round up, right? So how about 29.2 ohms? It's going to be 29.2 ohms for the resistance between those two. So I know that both of these together, I don't know the current going through them or anything like that, but I know that the equivalent resistance for both of these is 29.2 ohms put together. I also know that this one in the series part is just 20. So the second part is super easy. If I have the 20 ohm resistor and I have the 29 ohm resistor, I'm sorry, the 29 ohm equivalent resistance in the branch, the total resistance of all of it is going to be what? 40, yeah. 49.2, right? Because we're just taking them, we're just adding them together. 20 ohm resistor plus a 29.2 ohm equivalent branch or equivalent series counterpart is going to be a total of 49.2. So I'm going to say that the total resistance RT, I can say total this time, is going to be 20 ohms plus 29.2 ohms equals 49.2 ohms. I can now, if I have a voltage source, I can find the total current going through this circuit, and then we can break it down and we can find the individual currents going through it as well. So let's add some numbers here. Let's say that the voltage going through this source is 12 volts. So I'll say my voltage is equal to 12 volts. I think that's all we need because we can find it using Ohm's law. Do I need to draw out the triangle? Negative? Okay. So if I need to, I've got the voltage, I've got the total resistance. How do I solve for that? Okay, so it's going to be 12 volts divided by the resistance of 49.2 ohms, and that gives me my current, which looks like it's going to be a smallish number, which is good. Oh, let's go 3 decimals. 0.244 amps, Okay, well, and that's reasonable for a circuit. 0.244. Keep in mind your wall outlets are designed for 1 amp of current going out an individual outlet. But your circuits are made inside the walls as parallel circuits. So each outlet gets 1 amp, but the central branch gets more than 1 amp because it has to supply it to all of them. Okay, so we know that the total current going through here at the beginning is 0.244 amps. Now, what about this branch? Is it going to be 0.244 amps? Negative. What about this branch? Is it going to be 0.244 amps? Okay, so how can we find out what those are? Individually divide them? Okay, how do we know that it's 12 volts? Because you said it's 12 divided by 50. In a parallel circuit, the voltage across each branch is the same. However, we have a small problem. It's not 12. Yeah, so like here's the tricky part. Like normally it was 12, and I'm not going to argue that it's going to be the same in both branches, but it has to travel through the 20 ohm resistor first. So what we need to do is yeah, these two things are in series to each other, right? The first resistor is in series with the branch. So we can calculate the voltage drop of the first one, and then the leftover has to be what's in the other branches. Okay? So what's the voltage drop of the first circuit? Let's see here. I want to try to find out how much. I'm going to write delta V up here. I'm going to write out how much voltage gets lost in this. So we can do current times resistance, because we know the current is 0.244 amps, and we know that the resistance is 20, right? Okay, what does that give us? 0.244. I'm trying to squeeze that point in there. Okay, so we get 4.88 uh, volts. Yeah, we're going to subtract it away because remember, this is going from the resistor. I'm sorry, this is coming from the battery through the resistor. Okay, so this is not a positive 4.88 volts. This is going to be a drop of 4.88 volts. This load is generating some heat at the very least. If it's a resistor just by itself, the only thing it's really doing is just slowing down the current. And it's actually slowing it down to give enough of a drop in voltage down 4.88 volts. So the remaining voltage has to be 12 minus 4.88, which is what? Okay, so I know that the voltage here is 7.12, and I know the voltage here is 7.12, going across both of these branches. Okay, that was tricky. Um, so we can now do exactly what y'all were just saying earlier. We have the voltage and we have the resistance. We can find the current going through both of these in order to try to find the answer. Okay, so we can do the same thing that we did for the total current. I'm going to erase this part. If we need it, it's being recorded, so we're okay. Um, so and we've got the answer up here on the left side too. Okay, so we have a voltage of 7.12. We have a current of I don't know, and we're doing 50 first. Okay, I'll go ahead and call that branch 1, so I'll have an I1 down there. So the first current is going to be 7.12 divided by 50, and that comes out to be 0.143. Okay, rounding, 0.143, 0.142 amps. Okay, so I'm going to write that up here, 0.142 amps. And then the other one, we do the exact same thing. It's just 7.12 divided by 70 ohms instead. And that gives us a total current of 0.102. All right, so I'm going to write 0.102 amps here. You should be able to double check yourself because even if it is a compound circuit, the rules of the current still apply. So if you have a branch in it, these two added together should add up to the total current. So if I add together 0.142 and 0.102, I should get 0.244, and I think that actually does work out, correct? Okay, so we at least we can double check this. We know that we can get our answer correct because no matter what, you can't this is really just like the law of conservation of energy from science class. You can't create or destroy energy. If you've got electrons going through a circuit, you can't create or destroy electrons. Like you just can't have like, oh, there's an electron leak going over here. They're not just going to like bleed out, okay? You have to have the same amount of current roughly as what you started with, okay? In real life, those currents won't exactly match up. You'll be off by a couple thousandths, and that's just because you actually do have a little bit of leak out. It's just from heat and entropy and all that good stuff, craziness. Okay, so if you run a current meter through the first branch in this case and got 0.244, down here you might get 0.141 and 0.098 or something like that. They'll probably be a little bit lower. Okay. Chances are rare, unless your instrument is messed up, that they would be higher. That doesn't make a lot of sense. They're usually going to end up to be lower if you've got good instrumentation. Okay. If the that's a good question. What if the parallel circuit was first? The answer is it makes absolutely no difference. Our voltage would be the same. So hang on. Like what would be 12? Okay, okay. I get what you're saying. I get what you're saying. All right, so let's draw this out then. Let's just make this the other way around. So instead of having the resistor on the top wire, let's put the resistor on the bottom wire. The way that you solve it is very similar, but some of y'all are saying that we're going to get different answers. So let's investigate. We'll put the resistor here, and we'll put the resistor here, and then so the branch comes first, and then this part goes right here. Okay. Um, you know what? Let's do the exact same thing. So what was this? 50? 50 ohms, 70 ohms, and this was 20? Okay. So like this is the exact same uh numbers that we have before, the exact same resistors. We'll still use the voltage of 12 volts. The only difference is that we have a branch at the very beginning, and then we have the branch over here. We've already done some of this math, so we don't have to redo it. Like, for example, I know for a fact that the voltage drop going through this resistor is negative 4.88 joules. So I'm going to write delta V here is equal to negative 4.88 joules. Is everybody okay with that? The delta means change. So if I write delta V, that means just a change in voltage. That's also why I put a negative there, is I want to make sure that everybody knows that change in voltage is a negative 4.88 and not a positive 4.88. Because I mean, you could just as easily gain 4 volts here. You could be extra devious and you could put two batteries on this circuit, but you could put one of the batteries in the parallel branch just to be mean. Okay. Is that normal? Do people regularly do that? No. Can you? Sure. You can set this up any way that you want to. But you could actually end up with a positive voltage down here if you have multiple voltages input into the system. So negative makes a big difference to me. Um, are we okay with saying that that's negative 4.88 joules? It's going to be the same? We're okay with that? All right, what about the total current? Is the total current through this circuit going to be the same? How do I know? Yeah, it's the same numbers and it's the same configuration, because if you write it out like this, where you've got the branch going and then it closes up and then you've got the little series circuit on the other side, remember all we had to do is just add these two things together, right? Well, this total equivalence is not going to change. It's going to be the same number. And this resistor is not going to change. It's going to be the same number. So we just have to add them both together, and the total resistance is going to be the same regardless of which order that you had these put in. The total resistance is going to still be that, what was it, like 49.2 ohms? And I'm perfectly fine with that, because in series, you just add the two components together. What would become a problem is if you took the 70 ohm resistor and the 20 ohm resistor and you just swapped them. If you swapped them, everything changes because the branch current's going to change, the series current's going to change, and then we have a problem. Okay, that'll change everything. But if we just move that resistor from the top to the bottom, so far it's looking like everything is going to be the same. So I'm going to draw my current out. We are okay with the total resistance being 49.2, right? Are we okay with the total current then being 0.244? We're okay with that? Okay, because we could run the calculations again, but we're going to find out that it's going to just be the total resistance divided by the total voltage, or sorry, the total voltage divided by the total resistance, which comes out to be 0.244. So far, nothing's really changed. Okay, so now I think y'all's question was, what y'all told me was that it's possible that the current going through the branches might change, right? Okay, so let's do that. Let's calculate. What is the voltage going through the branches? That doesn't make physical sense. Okay, because like think about it. If you tell me that the voltage going through here is 12 volts, then what you're telling me is that you are breaking math because 12 volts and 4.88 volts doesn't add up to 12 on the other side. It adds up to like 16 something. So what you're saying is you're saying I have a parallel circuit that has no drop in it. There has to be a drop here. There has to be a drop. What is the voltage drop? Here, let's pretend that we don't know that it's 7.12. Let's pretend that we just like did not do that calculation and just were like, how can we find the total drop going through that? We have the equivalent resistance of the branch, right? This 70 plus this 50 is going to add up to a total resistance, a recce of not 70 plus 50, but it adds up to 29.2 ohms, right? Okay, so if I have a voltage equals current times resistance, and my resistance is 29.2 ohms, and my voltage is 12, what's 12 divided by 29.2? Okay, 0.411. I think I goofed up. Hang on, I gotta think about this. Yeah, sorry. I just actually calculated for a current of a theoretical voltage of 12. Sorry, that's exactly what y'all were telling me to do. That's not what we need to do. Okay, I just assumed that the voltage going through both of these branches was 12, and I got 0.411 amps, which is not true. Like, we know that that can't happen because our current's not going to double from our original. Our original is 0.244. So let me slow down my brain and let's recalibrate, right? Yeah, we know that this is 0.244 amps, and that we know that the resistance going through that is 29.2 ohms. Oh, 7.12 volts? Gee, that number sounds familiar. Yeah, the voltage going through each one of these, the voltage drop going through each one of these branches is 7.12 volts. I didn't mean to do it y'all's way by accident, but I ended up totally doing that and we got something very wrong. Okay, because if y'all assume that it's got a voltage going through the rails of 12 volts, that doesn't necessarily, that's an incorrect assumption. Okay? The voltage drop between both of these has got to be negative 7.2 volts, 7.12 volts. The delta V in this case would be negative 7.12. Okay, and the negative delta V down here would be negative 4.88. This makes logical sense because if you add the two drops together, negative 4.88 and negative 7.12 should add up to 12. Okay, so you've got a gain of plus 12 volts over here. You've got a loss over here. Okay, lesson learned, just because the branch comes first doesn't mean that there's no voltage drop. You can't say that that voltage going through there is 12. You have to look at the circuit as a whole, and you have to say, okay, well, this branch has a voltage drop going through it, and the voltage drop has to be the same for both branches, but it's not going to be the same number as the number of the starting point. Okay? Does that make sense? Okay, so are we all okay with the difference between having the resistor up at the top branch of series and the bottom branch of series is nothing? You could actually set this up either way and it would do the exact same thing that you want it to do. From an engineering standpoint, you would just have to determine which way is more convenient for what you're doing, you know. Um, I usually you normally see the resistor coming in first, and then it goes through the branch in and of itself. But that being said, I'm sure there are cases to where you would want to put the series resistor at the end. I don't know. It doesn't mathematically, it doesn't make a difference. And I'm sure if we got an electrical engineer in here that knew what they were doing, other than me who just like knows enough to be dangerous, they could probably tell you which way is preferred and why you would actually want to do it that way. As for me though, I have no clue. So just keep in mind, mathematically, it makes no difference. Yeah, technically, a toddler does know enough about electricity to be dangerous. But it depends. I don't know. Sometimes they touch wall sockets, and that's why you got to put the little plastic covers over them. So I don't know. There will be an assignment for it. Yes, I don't know if I have it posted up there yet, but I think there is an assignment for it. You can also use this using the table as well, because I think I've shown you guys the VIR table, right? Okay, for fourth period, I was actually going over using the VIR table, and you can do that as well. You just have to be really, really careful whenever you do that. And notice that on my table, on the right side, where it says current, I'm making sure that if it is a resistor and that part is in series, that it's going to be, I wrote a little S out to the side since that's a series component, and the R2 and R3, since they're in a parallel branch to each other, I wrote a P. The reason I do that is because remember in a series circuit, the currents are all the same. But in a parallel circuit, the currents are going to add up to whatever the current is coming into the circuit. Okay, so I had to write S and P out there just to make sure that we don't have any goof ups that go along with this. Okay, does that kind of make sense? Okay, do we want to try to solve this table out, and then I can let y'all. You think you're okay? Everybody thinks we're fine? Well, that means we probably need to do it. Um, it looks like whenever we did this one, we calculated out the total resistance and the total current going through the circuit, neither of which are actually available to us right now. So, like, this question would start like this with a whole lot of blank spots. We know that the total voltage in the circuit itself is 12 volts. We know that the resistor up top is 20, and we know that R2 and we know that R3 are 40 and 60. And we just saw that we could actually solve this system and using just our knowledge of circuits. But the table can also help us out a little bit too. So what we can do is we can use the formula to find the total resistance, and we can also use the individual currents to add them up and find out what the total is for the circuit itself. Where where would we start here? I would well, okay, okay. We got the VIR triangle. I'm gonna write it out. So we got voltage, current, and resistance. And we can use that triangle with any one of these down here. Um, can we find the voltage going through R1 right now? Do I have the current going through the resistor? I don't, right? I do not have the current going through the resistor. So since I don't have the total current, I don't have the current going through resistor 1. Okay, can I find the voltage of R2? Do I have the current? Okay, so the best way to look at this table is if you have two blanks, you can't figure it out yet. Okay, so we've got to get that information somewhere. We've got to get that information before we can use the triangle. Okay, so the best thing to do is look at the top right one. Do we have all of the resistors? If we have all of the resistors, then we can find out what the total resistance is, and then we can fill out the triangle from there. Okay, so like in this case, we have to use the formula for the equivalent resistance. So keep in mind that these two are in series with each other. The first one is 20 ohms. And then the other two, whenever you add them together, it is not 100. What is the equivalent resistance of the 40 ohm resistor and the 60 ohm resistor in parallel with each other? It is 1 over 40. You're right. 1 over 40 plus 1 over 60 equals 1 over Reki. We did, but we did it with 70. It was 1 over 40 plus 1 over 70. It was a slightly different value resistor. Yeah, I was doing this one. This one was from a different period, from fourth period Friday or Thursday. So it's a slightly different value. 1 over 40 plus 1 over 60. If you add those two together, you get 0.0417. 0.0417. And whenever you calculate currents or resistances or things in a circuit, I would probably go out to 3 digits that matter. In science, they call them significant digits. We're just going to say 3 digits that matter. That 0 in the front doesn't really matter. These three do. Okay, so 0.417 is going to equal 1 over Reki. So we just flip that. So 1 over 0.0417 is going to be what our answer is. So the equivalent resistance is, what do y'all get? Mine actually comes out 24 on the dot. Yeah. So that was convenient. So the 20 ohm resistor plus the 24 ohm resistor comes out to a total resistance of 44 ohms. Okay. Now what can we solve for? We can definitely solve for the total current. Okay, so we can use our triangle now and we can solve for the total current. So that's going to be the voltage divided by the resistance. Voltage divided by resistance. What does that give us? 0.27 amps. Is everybody okay with that? Okay, let's follow our circuit as we continue to go. Is the current going through the first circuit going to be 0.27? Because it's in series, right? So it's 0.27. I've wrote P down here for these. These are not going to be 0.27, right? But I can go ahead and I can find the voltage drop for the first resistor because now I've got two of the boxes. If I've got two of the boxes, I can use the triangle to find the third one. So it's going to be I times R, 5.4. So there's a 5.4 voltage drop there. Okay, that's going to give us these two resistors here that are going to have to be 6.6. Oh, yeah, because they have to add up to 12, right? So this is 6.6 volts. This is 6.6 volts. Ah. And now that we have the voltage going through both, we can now find the current going through both. They're not going to be exactly the same. They're going to be a little bit different. 0.165, okay. because that's going to be 6.6 divided by 40, and this one is 6.6 divided by 60.11 amps. So like if we add them together, that's going to come out to 0.275, right? Close enough. Yeah, so we got 0.270 for the top one and 0.275 for the bottom one. We're off by 5 thousandths of an amp. We'll for high school we'll be okay with 5 thousandths of an amp. The only reason you'd have to worry about it tremendously is if you are dealing with really, really sensitive components. Okay. So that's how you would use it doing the table instead. It's the same concept. It just gives you a better mental layout of where everything is by just writing out the voltage, current, and resistance on top, and then the individual resistors and the total on the left side. Okay. Y'all got any questions? How did I get the 44 total for the resistance? The equivalent resistance going through both of the branches is calculated by doing 1 over 40 plus 1 over 60, right? And that gave us a total after we flipped it of 24 ohms. Then, yeah, because you got to do 1 over that 0.0417 to get 24. And then 20 plus 24 is just 44. Okay. Yeah. Like whenever I do these, I have about a 15% chance of forgetting to flip that at the end. So like I'll calculate the equivalent resistance. I'll do 1 over 40 plus 1 over 60, and then I'll just leave the answer. A good way to try to remember that is it's always going to be less than the lowest resistor in the parallel branch. So I know it's going to be less than 40, but it's not going to be like way less than 40. It's going to be something like, I don't know, if you got a 40 ohm resistor and a 60 ohm resistor, you're going to have something like I don't know, between 10 and 30-ish, you know? And as you continue to calculate them, you kind of get a better idea on where your numbers are going to fall. But it's definitely not going to fall on 0.0417. You know what I mean? Because that's a super low resistance. You're looking for things that are like I think the resistance of just like wires by itself would be like in the hundredths of an ohm. So our resistors aren't going to be just like wires by themselves. So you just got to kind of keep that in mind. Any other questions? Okay. I will stop the recording and I'll give you all your assignment.